Okay, here we are once again. This is it. It's the Physics 2A video lecture 45. We're going to be talking about waves. I brought a couple of demonstrations in. But while I have your attention, we'll start with some announcements because this is the last lecture. It's going to be short, and I want to set us up for the final exam. So let's see what we have here. So announcements, final exam. So this is on Wednesday, December 16th. And I'll put down the official time on the schedule, 8:45 to 10:45. However, our final exam is really a double quiz. Okay, so what we're going to do is start it at 9 o'clock and end it at 9:30, and we'll have 2 questions instead of 1 as the other quizzes were, 9 to 9:30. So that's what it's actually going to be. It'll be on Canvas just the way we've been doing them before, 2 questions instead of 1. And I'll say more about what the questions are on through the hour here. So yeah, this is what you have to keep in mind. Wednesday, December 16th, 9 to 9:30 is when the quiz will actually be on Canvas. So 2 problems, 10 points each. So just like the other ones, and in fact, we're just adding points up. And at the end, I'll see which quizzes I drop and that kind of thing, the lowest scores I drop. Look on the syllabus for the whole grading scheme. The adjustments that I told you I would make will definitely be made, and they'll all go in your favor. Okay, so just keep working hard. But yeah, that's our schedule there. Wednesday, December 16th, 9 to 9:30. I should have everything turned in by Thursday, same week. Let's see what else we have here. Here's another note that I just saw there. Quiz number 8, 10 points for everybody. That was a while ago. Because there was some ambiguity there, or some problem, no problem. For us, though, 10 points for everybody. And yeah, we've been talking about oscillations. This topic of waves is also in chapter 13, so that's what we're going to wrap it up with. Okay, chapter 13, and well, since I have this on the board right here, these 2 problems, we'll take them from chapter 13, okay? From chapter 13, so that's the last 2 lectures and this one. And I'll put the list of the problems up, and maybe I'll do a couple of those as well. Okay. So good. Let's start on the subject of waves now. What is a wave? A wave is a disturbance in a medium, and you can imagine dropping a pebble in some water and you see the water waves propagate outward. And if you wait long enough, everything returns to the way it was. So the wave isn't really a transport phenomenon. It's not so much about material starting somewhere and ending somewhere else, as it's about the disturbance that actually moves through the medium. Okay, so a wave is a disturbance that's propagating through a medium. more than just that, because next semester you'll learn about electromagnetic waves, and they actually propagate through the vacuum. But we're going to start with the idea that there's a disturbance propagating through a medium, and our example was a water wave. And then I'm going to demonstrate some other things as well. I'll start with the water wave because you have a good feel for that. But here, actually, I'll demonstrate this next. Slinky. I'm not even sure if I'm spelling that right, but I brought one to class. That's this long spring. And it's a perfect example of what we think of as a wave. Namely, I'm just going to get a little disturbance, and you can see that disturbance propagate through. Okay. So, pretty sure that shows up on the video. Okay. So, after the wave is propagated through, the slinky is the same as it was before. So during the propagation of the wave, there seemed to be a little pulse, and actually I'll point this out. That pulse consists of a section where the density is greater. So it consists of a section like that, and that's the section that moves. Okay, so slinky's a good demo. And water wave slinky demonstration, and sound waves. Sound waves can propagate through air, they can propagate through water. So air, they can propagate through water. So through a gas, through a fluid, through a liquid. Both of those are fluids. Or they can propagate through a solid. Okay, so you can have sound waves, water waves. And then if we're talking about electromagnetic waves and light, things like that, radio waves, they're actually no longer propagating through a medium. So I'll put that there. So electromagnetic waves. Like I said, talk about that next semester. But we will note they propagate through the vacuum. Vacuum, no medium. Okay. So that's the first thing. And you can even add stadium waves and things like that as well. Everybody participates in the wave, but they don't leave their seat. Okay, so that is also a disturbance propagating through a medium. In that case, it's the entire crowd. It's good. So what I'm going to do next is draw the stereotypical wave and introduce the concepts of the wavelength and the wave speed frequency. So suppose we had that water wave. We think of a ripple like this, and in fact, the water wave's a good example. If you've ever been at the beach and the ocean and you're out behind the breakers, then a swell will pass under you, you just bob up and down. Okay? You essentially just move up and down, the wave passes under you. If there were a whole sequence of them, you would bob up and down in a certain sequence, a certain frequency. So let's just call this example the water wave. Not the kind that breaks and crashes, but the ripple type of wave. So we got a water wave here. These guys have to go. And This direction here, I'm going to say, is the direction of propagation. So it's coming from the left and it's moving to the right here. So that's our direction of propagation. And if you were to follow one of these crests here, you've got a crest, a trough, a crest, a trough, then it would be moving with a certain speed. So there's the direction of propagation here, and we'll say V is the wave speed. So we call V the wave speed, some number of meters per second. Okay, between two crests here, we have what we call the wavelength lambda. So lambda is the wavelength. Of course, that's measured in meters. Another Greek letter up. Have we had a lambda yet? Anyway, that's a lambda. Look it up on your table. Table of Greek letters, lambda. So there's the wavelength. And you can see, if we're going to have a wavelength, and we're going to have a frequency of this crest moving up and down as a train of waves moves from left to right. And so we immediately get the wavelength times the frequency is equal to the wave speed. That's a very general relation for waves. Wavelength times frequency is equal to the wave speed. So we had the frequency with our oscillations, okay? We didn't have a wavelength yet, but we had the frequency of oscillations. And we can think is, if the wave is coming here from left to right, and you're bobbing up and down, okay, then you're bobbing up and down with that frequency f. Okay? Vertical motion, essentially, as the wave passes under you. So this is just going to be that wavelength times however many times you bob up and down per second. Okay, so that's meters per second, and that is the speed with which the wave is propagating here from left to right. So the water wave, this shallow ripple type of wave, is a perfect example for talking about waves. Okay. So wavelength times frequency is equal to the wave speed. Now I have a nice device to demonstrate this kind of thing, and it won't be water, even better than water. Oh yeah, one more point, and that is that the motion of whoever is and whatever is, you know, on the surface of this wave, bobbing up and down, that motion is perpendicular to the direction of propagation. And when the motion, you know, this limited motion here is perpendicular to the direction of propagation, we call it a transverse wave. So I'll add that to our list here. Transverse wave. So the transverse wave, the displacements are perpendicular to the direction of propagation. It's perpendicular to the direction of propagation. And now, since I brought that up, I can revisit the slinky. And here you can see that these little displacements are in the direction, okay, along the direction of propagation. And that is called a longitudinal wave. So longitudinal wave you'll certainly find that in your chapter. Okay. Longitudinal wave displacement, and I'll just abbreviate. Displacement is in the direction of propagation. in the same direction as opposed to perpendicular to the direction. And of course with the water waves you see it really clearly. Something's bobbing up and down, the wave passes through. Okay, let me show you guys something that demonstrates that very nicely. We have a wave machine of sorts. Roll this in. Let's see if I can set it up in front of the camera. Okay. Okay, so this wave machine here, point at it, there is a wire that runs along the length of it, parallel to my ruler here. And that's what's actually going to support the wave. And then there are these rods that are perpendicular to the wave, to that wire there, and the wire provides a little stability. Now if I agitate this thing at the end, you see that disturbance propagate through. Very soothing motion, okay? Now, we have this relation here. We're going to think in this situation that the wave speed is constant, okay? That means that if the right side of this is constant, that means a short wavelength corresponds to a large frequency, and a large wavelength corresponds to a low frequency. And I can show you that on this wave machine really nicely. So a low frequency, you can essentially see the wavelength there. And calm this thing down. And now I'm going to agitate it more rapidly. You can see these ripples moving through. Those are clearly shorter wavelengths with a higher frequency. So that is right out of this expression. And you can even see that the speed with which the wave propagates, the pulse, okay, the pulse is essentially the same even if it's a large, long wavelength pulse or a small, short wavelength pulse. Okay, so yeah, this device is pretty interesting. It's also possible to set up what are called standing waves, but that takes a little practice. Okay, good. So there was our wave machine. Okay, I'm going to clear this and probably put it back up in a little more clear form. Okay, so summarizing, so far we have waves, and I will draw a horizontal line here. I can be a little more accurate now. Mark off. I can use another color. So how many wavelengths have I marked off here? This is a full wavelength, peak to peak, trough to trough. It just has to repeat itself, so that's 1 1/2 full wavelengths. Okay. And if I were to agitate the left side up and down, then this waveform will just propagate to the right according to the relation that I just had. So let's go ahead and once again, we'll put that lambda peak to peak, and we'll let this be the direction of propagation. I'll just write V here, and then we again have our lambda F is is equal to V. So again, the frequency is the number of beats per second if you're at a particular fixed point. Okay. For example, this would be moving up and down as I just demonstrated. So lambda F is equal to V. And the next type of wave I want to discuss is a wave on a string. This is important for musical instruments. And I'm not going to do anything fancy here. I have this long rubber band, and I have it under tension here. I'm just going to pluck it. Not quite sure how much this pulse will be visible, but I'm plucking it and I'm getting a pulse moving back and forth. If I decrease the tension, the pulse moves slower, possibly more likely that you can see it. If I decrease the tension even more, and if this thing just stops moving around, you can see the pulse, right? Now, so this is a transverse wave, and because it's only a pulse, we're not actually seeing this form. If I could pluck this thing with a high enough frequency, then we would actually be able to see a waveform like this. If this were the string on a musical instrument, and you pluck it, you'd hear a tone. That would be the frequency, right, that you're hearing, tone of a certain frequency. And there would be a waveform like this that under circumstances you can make visible, or if it's too small you can't really see it. Okay? If you have a guitar, you can pluck the strings and observe some of that. Okay, so this last section is waves on a string, and I think I can set this up right here. So let's call this waves on a string. And here the idea is the string is under tension. So string under tension T. I'll use T for tension the way we've been doing, but if we need to know the period's also T, so just be careful there. String under tension T, that's a force, and the mass per unit length. So when you have a string, the total mass is less important than the mass per unit length. Per unit length is going to be equal to we use the Greek letter mu, okay? And the units are kilograms per meter. Okay? So that's what we have with our string under tension T. We can think of this as an exaggerated version of it. We have a string under tension T, we pluck it, and we get this kind of bowed wave that then propagates. In fact, if it's under tension, but two fixed ends, it'll move back and forth. Okay, it'll reflect from one end, go back and forth. You kind of saw that with my rubber band right there. Okay, so I have a really nice derivation. This is a great one for the speed, a relation to the speed of a wave on a string. So next, speed of a wave on a string. And for that, I'm going to do a construction right here, very similar to what I have. So let's once again draw this, zigzag. Try again here. And on and on. What I'm focusing on now is this section of the string right here. And I'm going to imagine that it is part of, arc of a circle of radius r. Okay. And because of that, and then I would have an angle theta here, And then I have the tensions on the string. Tensions do, and I'm just taking an infinitesimal tiny element here, exaggerated my picture. So I have these tensions here and here, okay? So tension. But by construction, I'm going to do another color here. By construction, with respect to the horizontal, I have theta over 2 on both sides here. So theta over 2, theta over 2. And now we're going to ask, what is the force downwards? Okay. The force downwards, both of these have a downward component. That makes some room here. Both have a downward component, t sine theta. Actually, t sine theta divided by 2. So F net on this object is equal to 2 times t sine of theta over 2. On the other hand, that is equal to mass. Well, here, let's write it up this way. Right? F net equals mass times acceleration. Always a good way to start, right? Newton's law, nothing can go wrong. So, that net force is twice, because one from each side here, t sine theta over 2 pointing down. Okay, that's the mass. And what kind of acceleration is this? Well, in an instant, this is going to have passed through here to the right. Now it's going to be replaced by a horizontal line, and it's actually going to be replaced by a trough. So we can think of this as a circular motion, or a circular motion on an arc. So we can think of that as a centripetal acceleration. So that's why we say m v squared divided by r, with respect to that arc there. And now we get a great simplification because we're looking at small angles. We've got the small angle approximation. Let me go ahead and write that. Small angle approximation. We just used it the other day in talking about oscillations. So here goes again. Small angle approximation. We end up with 2t theta divided by 2. Now, this mass of that string segment there that I've bolded, that would be mu times r theta. In my way here, v squared over r. Mass per length, and then the arc length is r theta. Okay, so that arc length there is r theta, so that gives me the total mass. And then I have v squared divided by r. So this is too good to be true. 2's, of course, cancel. Theta cancels from both sides. R cancels. We're left with t equals mu v squared. Tension, mass per unit length, speed squared of the pulse. And I'm going to go ahead and solve that so that we end up with, actually I'll put a star here so I can showcase it. So we end up with V equals root tension, which is a force, right, over mu, which is mass per unit length. So that's the speed of a wave on a string. And now we can, here, I'll bring back this rubber band. So I can't control both of, I can't control both of these separately, but the harder, the more I pull on this, the more I increase the tension. and at the same time I decrease the mass per unit length because I'm thinning it out, so to speak, okay? So what we will see is as I increase the tension and simultaneously decrease the linear mass density, okay, the right side of this is going to get larger, okay, increase T, increase the denominator, and the speed's going to be greater, and that's what we had seen before. Okay, so I've got the very little tension, and I got the slower pulse. See how much this shows up on the video. I increase the tension, and I get the very rapid pulse. And if you've ever tuned a musical instrument, as you increase the tension by tuning it, you increase the tension, turning on the knob there, and what are you going to get? Increased speed. Let's go ahead and bring our formula back here. So lambda F is equal to V. So if we're talking about music, you're increasing the tension on the string, increases the speed. The speed is increased. The wavelengths are staying the same because you haven't changed the length of the string, and therefore the frequency is increasing. You get a higher pitch. So there you have the rudiments, waves on a string, and some of their applications. Okay, let's consult the clock. I think this is as far as we're going to take it this semester. So we had a pretty decent discussion of chapter 13, chapter 14, not at all. You guys can read that coming holiday. So yeah, we've taken it through chapter 13. Let me recommend a couple of problems here. These are homework not to be turned in, but to be learned for that final quiz, which is going to have, or that final exam is going to have 2 problems on it. Both problems will be from chapter 13. So in addition to the problems that we've already had, we're going to add 56 and 57. And these are problems with the speed of a wave on a string, and possibly also incorporating this. These are the two formulas we need in all of our wave discussion. Okay, the only 2 that we've really used. So we know about the difference between transverse and longitudinal waves, but that doesn't go into these formulas. This one is true for both types of waves. This is basically your transverse wave. In fact, definitely your transverse wave, because our derivation made use of that. Okay, so you have these 2 in addition to the ones that were on the prior 2 lectures. Since we have some time, I think I will go over a couple of these just to see what's there. 56, 57. I'll write down the total list. And then we'll look through these, maybe strike a couple, talk about what's important. Good, so what did we have? We had from chapter 13 problems. Chapter 13 problems. I'll just copy this list down here. We had in these last 3 lectures 1, 4, 10, 20, 33, 34, 35, 39, and now 56 and 57. I'll just consult the book here and see if I can give you guys some tips for these last topics. So, problem 1, I can make short work of some of these So one was a stretched spring, as you'll see when you look in the book, and force and acceleration. So when we stretch a spring, we've got a mass on the end there, spring constant K. So if we've stretched it a certain amount, remember we've got the force is a restoring force, so it's minus spring constant times the amount that it's been stretched. Okay. On the other hand, this same thing is equal to mass times acceleration. So yeah, that one was not difficult. Yeah, and then we have, for number 4, we're hanging something vertically, and the spring is stretching a certain amount. So there we're going to have K, I'll say delta X. You know, we use delta X and X interchangeably. So K times the amount it stretched is equal to the weight of whatever it was that did the stretching. Okay, is that what we had? Yeah. And in this case, the mass was the unknown. And number 10, equivalent spring constant of the bow. So there we're doing work equals 1/2 K. I'm going to write delta X squared like that. So this time you pulled a bow back under a reasonable approximation to Hooke's law. So there's our definition. And what were they asking us for? Yeah. They gave us a force, 0 to 230 newtons. So here we use and F magnitude equals K delta X. And 20, 33, 34. So yeah, once you have these basics, which is just forces, springs, accelerations, work, energy. So the next set of problems, we have omega equals root K over M for a mass on a spring. F equals 1 over 2 pi root K over M. T is equal to 2 pi root M over K. So you've got frequency, angular frequency, frequency in hertz, and period in seconds. Okay. So a lot of these problems you just have to see what's given and use these equations once or twice. Okay. So that was that other type of problem you want to be prepared for. And then we had the pendulum problems. What do I have here? And by the way, 33, that was a theoretical thing that we largely did in lecture. It's not the kind of thing we'll put on the exam, okay? Have a good look at it, but it's not going on the exam. So then we had pendulum problems. And I'll just say this about the pendulum. We talked about the physical pendulum. For the exam, we'll be talking about the simple pendulum. So for the simple pendulum, small oscillation frequency, you've got the length, you've got the mass on the end, but it turns out that that the frequency and the period do not depend on the mass. That's an interesting property in itself. Frequency is 1 over 2 pi sine omega, and period is equal to 2 pi root L divided by G. So there are different questions regarding the pendulum, and you're always using, these formulas here. These two are of course equivalent. That's the angular frequency, it's the counting frequency. That's the period. So, yeah. Good. And then the other two problems I just discussed, and you'll have a good look at those. They're interesting as well. And it's from this set and very closely related problems. I could literally use a couple of these. It's from these types of problems that will construct the last quiz, or the final quiz, if you want to call it that. Good. Good luck, everybody, and see you next time.